For your information, the first video I ever uploaded to the channel was about diodes, about how to measure them and how to read the information in the datasheet. In that same video I mentioned that left aside different types of diodes. Well, after 2 years, the day has come. In this video I present to you high voltage diodes. Anyways, I like to go step by step. So here I have a diode. It's an 1N4007, the typical silicon rectifier diode. And here I have an adjustable power supply. So you can imagine what are we gonna do. So you'll see. The matter here is that this power supply only can be adjusted from a little bit less of the main supplied voltage down to a minimum of 1.3 volts or so. And as you may notice, at that voltage the diode will be fully on. So it's obvious we need our voltage to go down to 0 volts. Nevertheless, truth be told, I'm not in the mood for designing a circuit for this, so we'll be running a much easier solution. We're gonna need some materials, a blue LED, the diode, and a 1 kilo ohm resistor. Now first of all, I want to show you why are we gonna need the blue LED. So I'll just hook it up with the 1 kilo ohm resistor to the supply, and let's see. By the way, if you ever wondered why we add a resistor to the LEDs, then I recommend you to watch this video. Well, back to the topic. As you can see, the LED lights up normally when I adjust the voltage of the supply. But let's do something. Let's measure the voltage across the LED, only in the LED. Look, the voltage it's about 1.8, 1.9 volts, and the LED it's off. Then I start increasing the voltage, and we can say that around 2.5, 2.6 volts the LED turns on. What I want you to notice here is the little margin between the LED on and off. With 2.4 volts the LED goes off, and with 2.6 volts it's fully on. Then we can say that the LED needs around 2.5 volts for turn on. I think you already understand what I want to get to. So here I have the rectifier diode instead the LED, and I'm going to do exactly the same that I did with this. As you see, the voltage across this when the power supply is at its minimum, it's around 600 millivolts. This means the diode is saturated, it's on. So if you still not get it, what I'm going to do is put the LED in series with the rectifier and the resistor. This for to be able to regulate the voltage from 0 volts, so we can see how the diode starts conducting current till it's fully on. Since the LED is there simply to create a voltage drop, then I'll just measure the voltage across the rectifier and the resistor. Therefore, we can totally ignore the LED. Now, if you see a negative voltage, it happens for some capacitive parasitic effects, but basically we're going to start from 0 volts and go on cranking up the voltage, and the LED is just there as a visual indicator of the rectifier being fully on. Now, if you need a visual reference, basically this is the circuit. So here I have everything wired up. The multimeter on the right, it's measuring the voltage across the resistor, and the multimeter on the left, it's measuring the voltage drop in the diode. If necessary to clarify, both multimeters are in the scale of millivolts. I emphasize again, if there is negative voltage being measured in the multimeter of the diode, it's only for undesirable effects. So let's just assume we're measuring 0 volts. So we start increasing the voltage, and both multimeters shows 0 volts. And as we can see, the first to register a voltage it's the one of the diode. Ergo, there is a voltage drop across the diode, but in the resistor there is none. So pause. What does this mean? Let's see. We are applying a voltage between the diode and the resistor, and in the diode begins to form a voltage drop that at the moment it's of 120 millivolts. Nevertheless, in the resistor there is any noticeable voltage. By Ohm's law, we know that any voltage difference applied to any device will create a current through it. And we have a voltage difference across all the circuit, across the diode, but there is non-voltage across the resistor. So there is no current circulating? What's going on? You'll see, the resistor isn't lying to us. Effectively, there is no current going through the circuit, even though we are applying a voltage to it. But this can be explained by this graph. Yes, you already know it. It's the graph of the diode, and in fact we already mentioned it in a past video, but never took the time to truly explain it. Let's see. First we need to learn how to interpret it. In the horizontal axis we have the voltage. If we move to the right, that means we are applying a positive voltage from anode to cathode in the diode. And if we move to the left, then we will be applying a negative voltage from anode to cathode. Now, either of these voltages would create a current in the diode, and just that is what we have in the vertical axis, the current that circulates through the diode. From the middle to the top means that the current goes from anode to cathode, and from the middle to the bottom means that the current goes from cathode to anode. Now, currently our diode is in forward bias, and we are applying a voltage from 0 to a few volts, so we should focus only in the second quadrant. Thus, it will give us the answer of what's going on. So let's not forget, this graph shows up what happens with the current when the voltage changes. If we see, the graph is telling us that at low voltages, the diode almost not allow current through it, and it's like this till a point around the 0.7 volts where the current shoots up. That's why there is no current going on our circuit. The diode isn't letting it pass, and it's actually acting like an open circuit. But this will only happen till a critical point gets reached, where the diode starts conducting and let the current go all on. Now you understand it, we can analyze the rest of the graph, which is in the third quadrant, although basically it's just a reflection of the second one, which means that we are applying an inverse voltage to the diode. But anyways, it's the same case as before. At the beginning, only a very small current can circulate. However, still there is a moment where if the voltage keeps increasing, the diode will let go a lot of current through it. The only difference is the amount of voltage necessary for this event to occur. In forward bias, this will occur between a few hundred millivolts, and in reverse bias, and depending on the type and model of the diode, this can happen from 100 of volts to thousands of it. And if you already forgot, this is the point of the video, the high voltage diodes that can withstand thousands of volts in reverse. So before fully go on the topic, this type of graphs are called current to voltage graph, and every electronic part have a characteristic one of this kind, so you can comprehend that these graphs are very important, and yes, we will study them in a future video. Now, for really deep understanding what are we doing, I want you to see it graphically too, and for that, obviously we're gonna use the oscilloscope. Thereby, here I have it set it up this way. The yellow line represents the voltage drop in the diode, and the blue line represents the voltage across the resistor. As you can see, first there is a voltage drop in the diode, and there is none in the resistor, just as the graph told us. Later then, the diode reaches its saturation voltage around the 0.7 volts, and now the rest of the applied voltage begins to fall in the resistor, and when we reduce the total applied voltage, we can see the inverse behavior. Now, let's replace the standard diode with the high voltage one and proceed with the same test. So, for you to see it, here I have both multimeters and the scope. So again, the left one measures the voltage across the diode, and the right one measures the voltage across the resistor, and the oscilloscope is set up the same as before, and just for the sake of it, the LED as an indicator. And stop. Okay, the LED is on, hence we can assume the diode is on. So let's analyze. First things first, we can see that the high voltage diode requires a much higher voltage drop to start conducting. We had to apply 3.7 volts, which is 5 times greater than in the standard one. Second thing to note, it's the slow transition from off to on. I mean, we could clearly see how the LED began to glow slowly, and even we can say that it isn't fully on, so... Here, we can affirm that the LED is completely on in 4.2 volts, so 6 times the voltage drop on a regular diode. But if we consult the datasheet of the high voltage diode, it states that actually at max load, the voltage drop in the diode can increase to 10 volts. So let's repeat all this, but when the diodes are reverse biased. Good. So again, we have the regular diode connected, but this time it's reverse biased. So let's proceed. And stop. The diode is reverse biased, and yet there is a current circulating, and it's large enough to make our LED glow. However, if we look at the graph, this shouldn't occur after until a large voltage applied. In any case, this happens because it's not a perfect diode and have a leakage current. However, what we care about is to compare it with the other diode. So let's replace it and do the same test. So here's the high voltage diode reverse biased, and yes, in the end there is a leakage current large enough to make the LED glow, but let's note that this time there was necessary a bigger reverse voltage to make it glow. Fine, so basically what we did was a parameterization of the diodes, but it will be better to see them in action. I mean, yeah, we stress them forward and reverse bias, but it would be a shame to don't put them in a real AC circuit. So for that, here I have a normal transformer. It has a secondary of about 17 volts AC, and what I'm going to do will be connect both diodes, now without the LED, and I'll replace the 1 kilo ohm resistor with a 20 kilo ohm resistor. So I'll just connect one of the scope probes to the diode, and that's it. Here we have our nice rectified semi-cycle. I will also add a probe to measure the voltage across the resistor. However, I want to clarify something. It's about how we made the first measures with the multimeters. We did it this way. So the logical will be to do it the same way with the scope, isn't it? Well, that would be a terrible mistake. Because even if I can't say that all the scopes, but the great majority of them have this part connected to each other. Thus, if we look at the diagram, we will be short-circuiting the cathode of the diode with the return line of the transformer, skipping the limiting resistor and letting a huge current run through the diode and our oscilloscope, putting in danger everything. The correct way to set up the oscilloscope for this type of measures is the following. Both negative clamps goes together in the same point, making this point our reference or virtual ground. So from this point, one probe measures the voltage across the diode and the other probe measures the voltage across the So finally, we make the necessary connections and we can see the waveform both of the diode and the resistor. The yellow one is the one of the diode and the blue one is the one of the resistor. And maybe you will be wondering, why are they phase shifted? Shouldn't be in phase? Well, it's very simple. Let's look at the diode voltage, the yellow line. When is the diode on? At the semicycle or at the valley? Exactly, at the valley. Don't forget that when the diode is on, in it only drops around 0.7 volts and the rest of the voltage falls across the resistor, just as you can see in the blue line. So those yellow semicycle peaks that we can see, it's actually the voltage that builds up across the diode blocking the reverse current, making it that almost no voltage falls across the resistor. Now let's proceed to do the same with the high voltage diode. But I want to ask you a question. Have you ever wondered where this graph comes from? Yes, from the current versus voltage, but where we can see it? Well, it comes from here. Let me introduce you to the X-ray mode of an oscilloscope. In simple words, the normal mode compares the voltage of both probes versus time. But in this mode, the oscilloscope compares the voltage of one probe against the voltage of the other. So here is where it comes such famous graph. Now you may be thinking why it looks weird. It's like it's only one side of the graph. Well, it's because the voltage is not large enough to make the diode conduct large enough reverse current. Nevertheless, yes, it should look like this. Actually, if we zoom in, we can see the important parts of the graph, like when the current starts growing in reverse and forward bias. Unfortunately, my scope is not good enough to appreciate the waveform, but I think it's enough to get the idea. So this way the video ends. Took me a lot more of time than what I expected. However, I'm glad we could dig in deep enough in the topics that not always are talked about. So if you liked the video, don't hesitate to subscribe, leave a comment, and I'll see you in the next video.